All right, we're going to be looking at related rates, okay? So I have some guidelines here, just some problem-solving techniques here. So maybe it might be helpful to draw a picture of what's going on and label any quantities. Obviously read the problem and identify all quantities. We can use a method called know, given, and find and fill in what we know. That might be an equation. Fill out what we're given and then figure out what we're trying to find. And then we're going to want to write an equation involving the variables with the rates of change that are either given or that we're going to find. And then we're probably going to have to use our implicit rules and chain rule to differentiate and then solve from there. So let's just go into it. So suppose x and y are both differentiable functions of t and are related by the equation y equals x squared minus 3x. Find dy dt when x is 3, given that dx dt is 2 when x is 3. That's a lot of information. So we are finding the derivative with respect to t. So I'm going to find the derivative of this equation and go from there. So the derivative of y is 1, but with respect to t, it's dy dt. X squared, derivative is 2x, but with respect to t, dx dt. And then I have minus 3x, so minus 3 dx dt. All right, so now I want to plug in what I know. So I know that x is 3. So dy dt is what I want to know. So x is 3. dx dt is 2. Oh, that's so funny. My grammar here is awful. Find dy dt when x is 3, given that dx dt is 2 when x is 3. That's extra information. dx dt is 2. So, all right, 2 times 3 is 6, 6 times 2 is 12, and 3 times 2 is 6. So in the end, dy dt is 6. All right, a pebble is dropped into a calm pond, causing ripples that form concentric circles. Circles is the key word here. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. So the radius changing, so dr dt is 1 foot per second. When the radius is 4, so radius is 4, at what rate is the total area changing? So we want dA dt is what we want to find. So I probably have to have some kind of equation dealing with area, right? And it's circles. So the area of a circle is pi r squared. So if I do derivatives, it's going to be dA dt. Pi is just a number I can pull out as a multiplier. And that's going to be 2r dr dt. If I want to find dA dt, that means I know everything else. So dA dt, I'm just going to rewrite this as 2 pi. R, we know that's 4. And then dr dt is 1 foot per second. So 2 times 4 times 1 is 8. So we'll have 8 pi. And if we talk about units, the radius is in feet. This unit was feet per second. So the rate the area is changing is feet squared per second. All right. All right. Air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. So that seems like a rate of change of volume. So dV dt, 800 cubic centimeters per minute. How fast is the radius changing? So dr dt, what is that? At the instant the radius is 30 centimeters. So I probably need volume of a sphere. formula. So volume of a sphere is 4/3 pi r cubed. So now if I do a derivative here, I get dv dt, and then I'd have 4/3 pi times 3r squared dr dt. These 3's will cancel out, so I'm left with 4 pi r squared dr dt. And what did I want to find? How fast is the radius changing? I want to find dr dt. So that means I know everything else. I'll move over here, give me some space. So dv dt is 800. And let's keep track of our units here. So 800 centimeters cubed per minute equals 4 pi. R is 30 centimeters squared. And then I'm solving for dr dt. All right. I'm going to divide both sides by 4 pi and that 30 centimeters squared. So that's 800 centimeters cubed per minute divided by, I'm going to get that number, 30 times 4 is 3,600 pi centimeters squared. Two factors of centimeters will cancel out, so I'm left with just one. The centimeters per minute is my units for my dr dt, and I probably want to reduce that 800 and 3,600. So let's see, those two zeros can go away, and then 8 and 36, I think we can divide those both by 4. So 4/9, and then don't forget the pi. So 4/9 pi centimeters per minute. All right. So the top of a 25-foot ladder sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what's the rate of change of distance between the bottom of the ladder and the wall? This is one where I'd probably draw a picture. So I have a 25-foot ladder. It's making a right triangle with a wall, right? Sliding down a wall at 3 feet per minute. So since we're going down, let's make that a -3. When the top of the ladder is 7 feet from the ground, so it's moved 7 feet, what is the rate of change of distance in the bottom of the ladder and the wall? I want this distance. So I want a dx dt, that rate of change there, if I consider this the x and y direction, okay? So with right triangles, let's think of a formula that we might be able to use. Pythagorean theorem should come to mind, right? X squared plus y squared. And in this case, we have a fixed value of 25. So 25 squared. And then I can do a derivative, right? That's going to be 2x dx dt plus 2y dy dt. And that's constant, so 0. I want to find the rate of change of the distance, so that dx dt. So that means I know everything else. So I have 2 times x. I need to find dx dt. Means I have y and dy dt. Dy dt, that rate of change is going to be -3 feet per minute, right? And then I need to know my x and my y. My y is 7 feet. I need to know my x. And I don't have that, but I can find it, right? I have that x squared plus y squared is 25 squared, right? And I know that my y is 7. So let's find what x squared is. So 25 times 25 is 625. Minus 49 is going to give me 576. And the square root of 576 is 24. All right, so now I can do some solving. So 2 times 24 is 48. 2 times 7 times -3 is -42. But I can add 42 to both sides, and then divide by 48. And 42 divided by 48 is, let's see, dx dt, 7/8. And it's a rate in feet per minute. All right. At noon, ship A is 150 kilometers east of ship B. Ship A is sailing west at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Okay, let me draw a picture. So at noon, ship A is 150 east of B. So here's ship A, and I guess we can put ship B over here. So distance-wise, east, we have 150 kilometers. Ship A is sailing west. Let me do my little compass. West. So we are moving this way. So that's left. So negative 35 kilometers per hour. And ship B is sailing north. 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? So I have a little triangle here, right? So Pythagorean theorem. We could do a squared plus b squared equals c squared. All right. We know the rate of change for each ship. So dA dt is negative 35 kilometers per hour. dB dt is 25 kilometers per hour. And we want to know dC dt. What is that? All right. Okay. Let's see the hour. So at noon and at 4 p.m. So time-wise, that's 4 hours. So we can find some other things. So for 4 hours, if we're traveling at a rate of 25 kilometers per hour, 25 times 4 is 100 kilometers. And I gotta think, 35. 35 times 4 is 140. So A is 140 kilometers. So distance-wise, if this whole thing is 150, we have 10 kilometers here. Might need it, might not. We'll find out. Okay. So now we want to find the distance. This isn't necessarily making a right triangle here. Oh, we can say, yeah, we can make it a right triangle. And we know that A is going to be, by the time it's moved, we're over here. So we have 10 squared plus 100 squared equals that C squared. So we have, what is that? 100. What's 100 squared? 100 squared is 10,000. And then we can find the square root of that. So let's see, 10,100. Oh, not a perfect square. So let's go a different route. So it's the square root of 10,100. I could factor out 100. And that would be 100 times 101. Yeah. Because then 100 is a perfect square. So 10 times the square root of 101 would be C. All right, so we want to find dc dt. So let's go ahead and do a derivative. So 2a dA dt plus 2b dB dt equals 2c dc dt. Now one thing I see is that each of these has a 2. So let's divide it out. So I'm left with a dA dt plus b dB dt equals c dc dt. And if I'm solving for dc dt, that means I know everything else. So a is 10, dA dt is negative 35, b is 100, dB dt is 25, c we just found was 10 times the square root of 101, and we're finding dc dt. So let's see what we can do here. That's going to be negative 350 plus 2,500 all over 10 times square root of 101. And let's see what that's going to give us. Negative 350 plus 2,500. I think that's divisible by 10. So it's going to be 215, and then divided by the square root of 101. So that's going to be about 21.4 kilometers per hour. All right. A right circular cylinder is changing shape. The radius is decreasing at a rate of 2 inches per second. So dr dt is decreasing at 2 inches per second, while its height is increasing. So dh dt is increasing at a rate of 5 inches per second. When the radius is 4 inches and the height is 6 inches, how fast is the volume changing? So we want to find dV dt. So volume of a cylinder is pi r squared h. So if I do a derivative, it's going to be dV dt. Pi is just a multiplier, and then I have to do product rule. Left d right plus right d left. I want to find dV dt, so that means I know everything else. So pi, it's a multiplier, so I really should throw that out front. R squared, so 4 squared dH dt was 5. And then I have 2 times h, which was 6. R is 4, and dr dt was negative 2. All right, let's see here. I have 16 times 5, 80. And then, oh, I guess that'll really be minus. 2 times 2 is 4. 4 times 4 is 16. 16 and 6. Is that 96? So negative 16. And then it's volume, so inches cubed per second. All right. An inverted cone is leaking water at a rate of 1 cubic centimeter per minute. So dV dt is -1 cubic centimeter per minute. The cone has a height of 9 centimeters, a diameter of 6 centimeters, which I don't know if we need radius, but radius would be 3 centimeters. Find the rate at which the water level is dropping. When h is 3 centimeters, given the volume is 1/3 pi r squared h. Okay, so maybe we need a picture. So we have a cone. Right, we have a radius and we have a height, right? Radius and height. So if I zoom in to what this might look like, right, we have a radius and a height. So we have a height of 9 and a radius of 3. So the ratio of radius to height, right, is 3/9, or really 1/3. And then that might be helpful here in a minute. So we have my volume 1/3 pi r squared h. I have a height of 3. I don't have a radius, so I probably want to solve this little ratio here for r in terms of h, right? So I can cross multiply. 3r equals h. So r is going to be h over 3. So that way I can take my volume equation and make that an h over 3 squared times h. So clean this up. We got volume is 1/3 pi, and then this would be h cubed over 9, which I can combine with that fraction. So the volume is really 1/27 pi h cubed. Then I can do a derivative. I'll move that over here. So dV dt, 1/27 pi times 3h squared dh dt. So dV dt was -1. 3/27, I can make that 1/9 pi. H, we know, is going to be 3. And then dH dt is what we're solving for, right? The rate at which the water is dropping, so dH dt. 3 squared is 9, so those actually cancel out. So I have -1 equals pi dH dt, and then I can just solve that by dividing by pi. So -1 over pi. And dH dt, so that's going to be centimeters per minute. All right. We have, this last one here. A lamppost is 26 feet above the sidewalk. Joe is a 6-foot tall calculus teacher and is walking away from the lamp at a rate of 4 feet per second. When he's 20 feet away from the lamppost, find each of the following. How fast is the length of his shadow changing? And then at what rate is the tip of his shadow moving? Okay, so let's make a picture. So I have a lamppost and I have a guy, right? So, and he's walking away and making a shadow. He is 6 feet tall and the lamppost is 26 feet tall. And if I think shadow, his shadow is going to be here. So I have 2 triangles, right? I've got this one triangle, but then I also have this triangle here, okay? So I have some distance here. Well, we can call that X. And I have some distance here. I'm going to call that Y. Okay? So if I do similar triangles, I can do the heights. So 26 is to 6 as the big length. So X plus Y is to the little length, Y. Right? And then I probably want to cross multiply. So I've got 26y equals 6x plus 6y. Solve for y. So if I subtract 6, I get 20y equals 6x. Divide both sides, and I get 6x over 20. I can divide both of those by 2, so 3/10 x. Okay. And then I can probably do derivative from here. So that's going to be dy dt equals 3/10 dx dt. And what did we want? What else do I know? Let's see. He is walking away at a rate of 4. So this x value is what is changing here. So dx dt is 4. I'll write that here. dx dt is 4 feet per second. So then the length, his shadow's changing. So this one here is going to be, what is that, 12/10? But I can reduce that to 6/5 feet per second. Right? At what rate is the tip of his shadow moving? So at what rate the tip of his shadow is moving is going to be just the rate of change, the sum of the rate of change of those two pieces. So we know what dy dt is. We just found that. So 6/5. And dx dt was given to us. So let's add those. That's going to be 20/5 plus 6/5, which is going to be 26/5 feet per second. All right, that is all. So if you have any questions on related rates, let me know.